Welcome to the fourth lecture in this series of lectures on RTL modeling with Verilog. I am Harish Ram and my assistant is Jayanth Balaji. In this lecture, we shall introduce you to Dataflow modeling and behavioral modeling styles in HDLs. In the previous sessions, we have given you an overview of structural modeling styles. We have seen that structural modeling styles don't provide any significant reduction in design effort. They are recommended only for top-level integration of building blocks in a design. The real power of hardware description languages can be exploited only if we learn how to model digital systems at the behavioral level of abstraction. In between the behavioral and structural modeling styles, there is another level of abstraction called the Dataflow modeling. In Dataflow modeling, the systems are described based on their Boolean equations. Thus, the Dataflow modeling style provides a small reduction in design effort compared to the structural modeling style. So, in this lecture, we will take you through a few examples in Dataflow modeling and finally wrap up with an introduction to the behavioral modeling level of abstraction. We will visit the half adder again to illustrate Dataflow modeling. So in this example, we have modeled the half adder using Dataflow equations. You can see from this example that for implementing a model of a digital system at the Dataflow level of abstraction, the designer is expected to be conversant with the Boolean equations that model the signals that are to be driven through the output ports. Therefore, this modeling style represents a small reduction in design effort when compared to the structural modeling style. Proceeding further, this example shows a full adder which is implemented using Dataflow model. Unlike the previous style, the structural modeling style, where we had instantiated two half adders and a couple of gates for realizing the full adder, here we are driving the output signals directly through the assign statement, and the output signals are assigned through the Boolean equations which are used for modeling the sum and carry outputs. Finally, we have the ripple adder, which is realized using a set of identical Dataflow equations. Here, of course, in addition to the input and output ports, we need an internal wire C for realizing the intermediate carry stages. At this point, you can try out a small exercise which involves realizing a Dataflow model for the 4-bit binary to gray code converter. The modeling style will be similar. You will have 4 equations which correspond to the models for the 4 output ports representing the 4 bits in the output gray code. Here we illustrate how Dataflow modeling styles can be used to model systems at the behavioral level. There are some very limited provisions for modeling conditional behavior using Dataflow statements, as the first example illustrates. So here we have used a conditional statement using Dataflow modeling for modeling a 2-input mux, a 2-input multiplexer. Slightly more complex behaviors can also be modeled using Dataflow, as illustrated by the second example, where a conditional statement which is a little bit more complex is used for cascading 2 multiplexers. But as is evident from these examples, Dataflow modeling is inadequate for modeling very complex behaviors. So therefore its utility for the designer towards saving design effort is very limited. With this, we conclude the discussion on Dataflow modeling. Now we will move on to behavioral modeling. In fact, we will spend considerable time in this course trying to understand what behavioral modeling is all about. In fact, as I mentioned earlier, behavioral modeling lends hardware description languages their real power. So in this level of abstraction, in the behavioral level of abstraction, designers are able to model various digital subsystems based on their behavior. This spares the designer the painstaking task of trying to map the behavior of a digital system into a set of Boolean equations and trying to implement them using a set of target gates. We will be primarily concerned about writing RTL or register transfer level behavioral models, and here our objective will be to write what is called synthesizable codes. That means eventually the models that we write should get synthesized into a gate level netlist, which will be finally targeted towards an ASIC or FPGA library. This means that we should write only synthesizable codes or use only synthesizable constructs in our HDL codes. There are a lot of non-synthesizable constructs which are also provided in hardware description languages like Verilog and VHDL. These include delay constructs, X values in assignments, and variable indices in loops. These constructs are primarily meant for verification. They are required when we write test benches and also simulation models which are used to verify designs. Till this point, we have been acquainted only with the concurrent assignment statement, which assigns a particular signal in a concurrent block. The assignment statements in a concurrent block, as the name implies, they execute concurrently. That means the order in which these statements appear in the code is of no significance. But we know that the behavior of digital systems basically map into conditional statements of the if then else type, and these statements can be modeled only if we have some provision for writing or specifying conditions in a sequential fashion. That is, if some condition 1 is true, do this, and if it fails, do something else. So basically, for modeling a conditional behavior, we need to have some constructs which can model a set of conditions which are examined in sequence. So we look for a first condition, and if it is not true, then we look for the second condition, and so on. So for facilitating execution of conditional statements in hardware description languages, we have what is called the sequential blocks. Here the term sequential basically refers to statements which execute in sequence. They are not to be confused with sequential circuits. In Verilog, sequential blocks of code are created using the always block. We had briefly introduced the always block in the first lecture itself. Here I have shown two always blocks. The first always block models a 2-input OR gate. Of course, it's a very trivial always block, because we know very well that this particular behavior can be modeled easily using an assign statement. But here, of course, I have included this always block just to illustrate the structure of the block. The second always block that is shown here, it is not so simple. It models the behavior of a 2-input multiplexer. We know that the behavior of the 2-input multiplexer directly maps into a very simple if statement. So if the select line is 1, you assign the output to the first input, and if not so, you assign the output to the second input. So this behavior, which we describe in natural language, can be easily mapped into a hardware description language behavioral block using an always block in the case of Verilog. So this is a very simple illustration of how we model behaviors of digital systems using behavioral code. It has to be kept in mind that any assignment that we make inside a sequential block can be made only to a signal which is declared as a reg. This means that all the signals we assign inside an always block have to be declared to be of type reg. This slide illustrates the effect of ordering of statements in a sequential block of code on the hardware that is synthesized from the block. Here we have modeled a cascade of two multiplexers which are controlled by two independent select signals, cell 1 and cell 2. In the first block, the signal cell 1 is checked first, followed by the signal cell 2. Now this translates into a cascade where the first level of multiplexer is controlled by the select line cell 1 and the second level by the select line cell 2. In the second always block, the conditions are swapped, which means that the signal cell 2 is now checked first and cell 1 follows cell 2. Obviously, this translates into a different hardware where the first mux, the first level of mux, is now controlled by the signal cell 2, followed by the second mux or the second level of multiplexer, which is controlled by cell 1. So this simple example, I think, will serve to emphasize the importance of proper ordering of sequential statements. Later on in this course, we'll take up some more examples where the ordering of statements can completely result in totally different hardware being synthesized from the code. Multiple always blocks can exist in a piece of code. These always blocks are similar to concurrent statements, which means that all these blocks, they execute concurrently. The always blocks can communicate among themselves through internal signals of type reg. For instance, in the example shown here, the always block 1 assigns a signal called out1 through some statement, and this signal is read by the always block 2 as indicated by the presence of the signal out1 in the sensitivity list. Now when these blocks are synthesized into hardware, there are two blocks which are synthesized corresponding to the block 1 and block 2. Therefore, the out1 signal, which is driven from the always block 1, forms the output of the hardware synthesized from block 1, and this being read by block 2 forms one of its inputs. So this basically illustrates the fact that multiple always blocks can exist, will exist in a piece of code, and they will execute concurrently, with communication being between these blocks being facilitated by the internal signals of type reg. Now to sum up, the always block provides the framework for behavioral modeling of digital systems. The behavior of a digital subsystem can be modeled using sequential statements. Here the term sequential refers to the sequential execution of statements inside the always block, and it is not to be confused with sequential circuit behavior. Designers are expected to use synthesizable constructs while writing behavioral RTL models. The ordering of statements in a sequential block impacts the hardware synthesized from the code. Therefore, designers have to be careful to ensure that the statements are properly ordered so as to reflect the behavior that is expected from the block that is designed. Finally, concurrent always blocks will exist in a code. These always blocks will execute concurrently, and they can communicate among themselves through internal signals of type reg.